Here this circuit converts AC to DC, AC to DC. Okay, here we are using R load, means any incandescent bulb kind of load we are using. Okay, so this is one AC to DC convert. Okay, here 4 SCRs we are using. T1 and T2 we turn on simultaneously in positive half cycle. T3 and T4 we turn on simultaneously in negative half cycle. In positive half cycle, T1 and T2 conducts, so current flows in this way, in this way, in this way in positive half cycle, because we in positive half cycle, after we apply the gate pulses to this T1 and T2, T1 and T2 starts conducting, later currents flows in this direction. Okay, so this continues till 180 degree. Again, in negative half cycle, if you fire T3 and T4, then so in negative half cycle this side is positive, so current flows in this way, then it flows like this, so we can say that after application of the gate pulses to T3 and T4, T3 and T4 will turn on and it will start conducting the current in negative half cycle. Okay, so this is a simple circuit. We can see the waveforms here. This is an input voltage which we have applied, which we are taking from the secondary of the transformer. Listen here. Here we should consider that there is a transformer. Primary is connected to the power supply company, sockets, which is there in our wall of our home or somewhere. Then secondary of the transformer is connected here. The secondary of the transformer I am considering as a AC source for this circuit. Okay, so whatever input we are applying here, I am showing using this waveforms. Here you can see, here we are applying like nearer to 325 volts peak. It will take a maximum of, in this case it will take a maximum of 325 volts peak. Okay, minus and it goes back to minus 325, it will change. Okay, so this is my input. Okay, next, why we are getting a load voltage like this? Why the load voltage is 0 from here to here? That is very important. See, this axis is 0. Okay, then this is 40 volt. You can see here this is minus 40. Okay, so middle point is 0. So because now we are in the positive half cycle. So if I go back in the positive half cycle, T1 and T2 conducts only if you apply the gate pulses. So here, somewhere here we have applied a gate pulses. That's the reasons T1 and T2 starts conducting. Then if T1 and T2 starts conducting, it is acting like a closed wire. We can see here current flows here. So if you find a load voltage somewhere here, same as whatever voltage we are getting from this AC source, whatever voltage we are getting from this AC source. So load is receiving this AC voltage, this input voltage once T1 and T2 starts conducting. That's the reason here T1 and T2 starts conducting here, starts conduction only after this firing angle. That's the reasons load voltage begins somewhere here and it continues till here. This is an end of half cycle. This is an end of half cycle somewhere here. This is an end of half cycle. Then again in the negative half cycle, okay, input goes to negative half cycle. Again somewhere here all the SCR is in off state. All the SCR is in off state. T1 and T2 is also off, and your T3 and T4 is also off. Why T3 and T4 is off means we have not applied any gate pulses to these two. Okay, so once T3 T4 starts conducting, then see here we are in the negative half cycle. This side is plus goes plus, current flows in this way, comes back. So in previous half cycle also current direction was in this way, and now also current direction is in this way. So we are getting in positive half cycle and as in negative half cycle the current with respect to load side is same. Okay, that's the reason again load is receiving the input voltage from somewhere here. Here we are applying a voltage as to pulses to gate of the T3 and T4. Okay, which to T3 and T4. Okay, this is a load current. You can see here what is the load current. Here the load is resistor. In the resistive load, the current is just voltage divided by R. Current is in phase with voltage. That's the reason current is in phase with voltage, and just voltage divided by resistance. So you can see here this waveform is and this waveform is in phase. So load current also starts wherever load voltage starts. So same waveforms, but the magnitude wise this it is showing something like 325, somewhere around 325. This is 325 divided by what is the resistance value we have chosen here? This value 10 it seems. I can show you this is circuits. So it's 10. It is 10. Okay. So now, then, okay, I will come back to this source current later at the end. Next. So first, before that, I will show you the simulation of these circuits so that you can, in a better way, you can understand. Okay, I will go to LT Spice simulation. See here. Try to understand. I don't know whether this is an AC source. This is AC source. Listen here. It is connected to this SCR. 4 SCR is there. See here, I told in your previous circuits I have not shown the gate voltage just for simplicity. Here I have shown, because if you want to implement such rectifiers, we require 4 such gate voltages. Means a pulse generation circuit is required. It should give pulses to gate. Always assume that if this is a pulse generation circuit, that this positive I should connect here, the negative terminal I should connect here. If you are generating a pulses from microcontroller 1 pin I am connecting here, and ground of the microcontroller I am connecting here. Okay, if this pulse is from your RC firing circuit, or if it is from UJT firing circuit, you have seen so the pulses positive I should connect here and negative should connect here. Okay, you just remember that, try to understand that. Now This is pulse generation circuitry. So this pulse is changing from 0 to 7 volt. Okay, 7 volt. I will show you rest things later, its characteristics. See here, this SCR and this SCR should turn on simultaneously. So for this SCR also we have connected one more pulse generation circuit. This is one more pulse generation circuit, one more pulse generation circuit. Pulse should be connected to gate of the SCR, and to another negative should go to cathode of the SCR. Here we have a bridges, 4 SCR bridges and 4 pulse generation circuitry, and bridge should be connected to load. Okay, I will show you one waveforms of this. See here, maybe you will understand the whatever I have shown the previous. Okay, I will simulate the circuits. So whatever this is my input. This is your input. See here, it is input is changing from 0 to 325 and coming back to this. Only one waveforms I will show you. Okay, so then okay, understood now. So I will delete this right now. Then see this SCR and this SCR. Okay, right now I will show you both. This is the gate pulses. Okay. Right now I will show you input voltage and also gate voltage. Okay, this is the voltage which we are applying to SCR1, and a similar voltage we are applying to SCR4. Okay, then see here, see when exactly I have applied here, this is 4 milliseconds. So 0 to this is somewhere around 2 milliseconds I have applied. See, I can show you both. This second time when I am, this is first stop cycle 0 to 20 milliseconds. Again the next stop cycle, again after 10 milliseconds one more pulse I am applying to the thyristor T1. Okay, see this pulse and these two pulses same. See, I have written 0 to 7 volt, it goes to 0 to 7 volt, 0 to 7 volts. See, this is characteristic of pulses. See, when it initially it is in 0, then it goes to 7, and in this 7 volt it will remain for a how many milliseconds? Here it is remaining for 2 milliseconds. So that is pulse width I have chosen 2 milliseconds. It need not be 2 milliseconds, it may be 1 millisecond or anything else. Then it goes come back. So in SCR we have learned that there is no requirement of continuous gate supply. Gate we should give supply to gate until current is more than latching current, then it remains 0, goes to 0, then it remains in 0 after after 20 milliseconds. See, somewhere here this is at 2 millisecond, this is at 22 millisecond, one more pulse comes. Why? Because the same SCR, this SCR works once again in the next half cycle. So now I will show you both input voltage along with your this is input voltage. See, this is because 325, this is 7 volt, it is very small, so it is showing like this. So in the first half cycle, somewhere here we are applying a gate voltage. Again in the next half cycle we are not applying gate voltages to the T1. In the very next cycle we are applying the voltages. Okay. So I will show you the voltages whatever we have applied to another these two SCRs. I can show you this voltage or something else. Okay. Show you when exactly we are applying the voltage. See, here red color, whatever I am showing here is red color. This pulse is we are applying to the T3 and T4 at the negative half cycle. See here in the next negative half cycle. So this is in the positive half cycle. So in this way we should apply gate voltages to the SCR. So I can show you the load voltage. Only I will show you the load voltage to you. So where we should get a load voltage? Here. Load voltage. See. Load voltage. Whatever this is load voltage, see here, this is my load voltage. Load voltage begins exactly when my now shall I remove the input voltage or remove. You can see here I am applying gate pulses to the T1 and T3. So load voltage starts here and it is in sinusoidal there onwards. Yes. Then in the next half cycle we are applying gate pulses to another. This red whatever is square like thing is gate pulses. So that branch starts conducting, then load voltage starts like this, it comes like this. Okay. So if you want to check the load current, this is a load current. You can see this is also sinusoidal there onwards. Okay, see, you can see load current is also sinusoidal because it is in phase with voltage. So try to understand the circuits. Okay, here just for your simplicity I have not shown the gate pulses. You can show gate pulses in a separate row. If you are showing the gate pulses, one gate pulses you should show somewhere here, and in the second row we should show another gate pulses somewhere here. Okay, now I think I have tried to familiarize the circuits now. If you check the circuits, I think see simple, T1 and T2 conducts in positive half cycle after application of the gate pulses, and through current flows through that, load will receive the sources through T1 and T2. T3 and T4 conducts in the second negative half cycle if you are applying the gate pulse after application of the gate pulses to T3 and T4. So through that current flows, so that's the reason load receives a power through T3 and T4 from AC source, from this source. But in the load side, the current direction is same. That's the reason I say it is a DC. Current direction is same. Current will never take negative value, but current is fluctuating. Voltage and as well as current is having a fluctuation. Doesn't matter. Next. What is if somebody, then your question is, so you said we have converted AC to DC. If I keep a multimeter somewhere here or DC voltmeter somewhere here, DC voltmeter somewhere here, we need to take the average output voltage of these waveforms. Listen here, we need to take average of these waveforms. This is one periodic waveforms. This is a period of that. See, this is a repetitive pattern. It repeats again and again. That's why I am saying that here to here it is one period. In a periodic waveforms, if you integrate one period of that, and if you divide that value by its period, then it is giving you the average. So I need to integrate from here to here. This starting angle I will consider here onwards alpha, means starting angle in the sense the starting time when your SCR T1 and T2 starts conducting, that is alpha. Okay, alpha, and it ends at pi. That's the reason I am integrating from alpha to pi. And what is the mathematical model of these waveforms? Mathematical model of this waveform is, see, this waveform and this waveform mathematical model is same. This is Vm sin omega t. So this is also Vm sin omega t. From where? From alpha onwards till pi, this waveform is behaving like a sinusoidal waveforms. Okay, that's the reason mathematical model is Vm sin omega t. And what is the time, average time from here to here? It is pi. That's the reason we are performing the we are calculating the DC value of that waveforms in this way: 1 by pi alpha to pi Vm sin omega t d omega t. Here almost just maths. Sin omega t integration minus cos omega t alpha to pi minus cos pi minus of cos alpha 1 plus cos alpha Vm by pi. Okay, so we got Vm by pi. 1 plus cos alpha is an average value of the load voltage. And what is an RMS value of the load voltage? Same waveforms we need to take RMS value. For the same waveform, this waveform only we need to take RMS. RMS means root means square. We need to square these values. We need to take mean of that and we need to take root of that. Here RMS, root, mean is 1 pi square Vm sin square omega t whole square. 1 minus cos 2 omega t by t, 1 minus cos 2 omega t minus cos 2 omega t integration sin 2 omega t by 2. So then just apply limit, just mathematics, pi minus alpha omega t is pi minus alpha, because pi is substituted here, then sin 2 pi by 2 sin 2, this all. Finally you got like this.